It's 13.8 billion years ago, and you are nothing. You aren't even close to being anything yet. In fact, all the stuff that makes up you and everything you see around you doesn't even exist yet. But that won't be for long, because in a fraction of a second, you're going to burst into existence, along with every star and galaxy in the observable universe during the Big Bang. And when you do, you'll find yourself in an ever-expanding cosmos. Since the moment you popped into existence, your cosmic address has been getting bigger. Even now, as we speak, you are drifting away from every single thing that has ever existed or ever will exist. Don't believe me? Here's the proof. When Alexander Friedmann first proposed his namesake solution to Einstein's equations of general relativity in 1922, it was only one of 3 possible models for the universe. It could be open, meaning infinite in size, closed, meaning finite but infinite in volume, or static, meaning unchanging in time. This last one was the prevailing model at the time, because it seemed to match observations best. But Friedmann's solution offered an alternative, a universe that changed in time. If the universe was expanding, then yes, there would have been a beginning, and if the matter within it was spread evenly enough, it would look like the universe was infinite in size. It would also explain why certain galaxies seem to be flying away from us faster, the farther away they were. But here's where things get strange. According to Friedmann's model, those receding galaxies would be doing exactly what we observe them doing today. So the model fit with observations. But that doesn't mean it was correct. At the time, nobody knew whether or not the universe was actually expanding. But then in 1929, a man named Edwin Hubble made an astounding discovery that solved this problem, found that every galaxy in the observable universe was indeed flying away from us, and the farther away it was, the faster it seemed to be moving. This meant that there really was an expansion to the universe, and Friedmann's model was proven correct. Hubble's law revealed that the universe had started out much smaller than it is today, and is still growing, which means that the address of every galaxy in the universe has been getting larger. If you're sitting in London, England, your address might be 42 Baker Street. But in another universe, maybe that same person lives at 42 Baker Street. Or if you live there, you may be at 42 Baker Street. Or if you live there, you may be at 221B Baker Street. Though probably not, because that's Sherlock Holmes's address. Point is, if you're living at 42 Baker Street in another universe, your address is still 42 Baker Street, but the distance between you and every other object has been increasing. Sports. You are drifting apart from everything else, including the Earth and everything on it. That means that the 42 Baker Street in this other universe is flying away from the 42 Baker Street in our own. And if you want to know how fast you're drifting apart, all you need to do is multiply the number by how far away it is. And unfortunately for my hypothetical flatmate, they're pretty far away. I know that sounds kind of weird. Like if you're on Earth, how can you drift apart from the Earth? But think about it this way. Say the universe began with only the Earth and you on it, and then expanded to include just the solar system and nothing else. Even if you stayed put, the Earth would fly away from you as the space in between the two of you got bigger. Now, imagine adding more planets to the solar system. As the universe expands, the space between you and each planet gets bigger, so every planet flies away from you. And when you throw in some galaxies, it's the same story. The farther away something is, the faster it recedes, because the more space there is to expand. In a way, this just makes sense. If the whole universe is expanding, then everything in it should be expanding too. And if it's expanding in all directions equally, then it should look like the universe is infinitely large. But that doesn't quite work either. That's because if the universe really were infinite, then eventually it would have to start repeating itself. This issue was pointed out by none other than Stephen Hawking in 1970. And since then, cosmologists have come up with a couple of different ways to visualize this phenomenon. One of the more popular ones is called a dodecahedral space, which, well, I'm not gonna lie, I don't really understand it. But the basic idea is that if you were to take a triangle and cut it along one edge, you'd have 2 smaller triangles. Do that again with each of the new edges and you end up with 4 triangles, and then 8, and then 16, and so on. You've doubled the number of triangles every time you cut one. If you kept this process up, you'd end up with 2 to the 12th power, or 4,096 triangles. Then, if you took the original shape and colored it one color, and the new shape's the same, but shifted by one color, you'd end up with a tessellation, which is just a fancy way of saying that all the shapes fit together, without any gaps or overlaps. And if you extended that pattern infinitely in all directions, it would be periodic. And that's basically what a dodecahedral space is, a hyperbolic space that has a repeating pattern that never ends. But you're not a hyperbolic space, and you don't live in one either. That's because we live in a spherical space. And to visualize what that looks like, all you need to do is take a flat sheet of paper and wrap it into a cylinder. Now, if you move far enough down the cylinder, say halfway around the world, then back up again, you'll find yourself at the exact same point you started at. What just happened? Well, you completed a geodesic, which is just a fancy way of saying you traveled along the shortest path between 2 points. And in a spherical space, if you travel along a geodesic far enough, it loops back around to where you started. In fact, every geodesic in a spherical space does that. Now, don't freak out and start thinking we're on a giant sphere in the middle of nowhere. There are other spaces that have this property too. For example, if you took a flat sheet of paper again, but folded it into a cylinder and then cut it along the fold lines, you'd end up with a bunch of shapes like these. And if you continued traveling along a geodesic past its apparent endpoint, it would loop back around to where you started, too. We call this kind of space a torus, which is also what we call those donut things. Actually, they're technically called a Klein bottle, but the shape you get when you wrap a flat torus around itself is called a Klein bottle, not a torus. What's the point of talking about all this? Well, as Hawking pointed out, the universe can't be infinite, because it would be too boring. Galaxies would eventually start repeating themselves. So the universe must be a torus, right? Well, not exactly. Remember how in a spherical space, geodesics eventually looped back around to where you started. That doesn't happen in a torus. So if you lived in a torus and decided to leave home and walk straight towards the sun, you'd never get there because eventually you'd find yourself walking next to a duplicate of your house. But we know that's not happening. If you left Earth and walked straight towards the sun, you'd never make it because you'd get burnt to a crisp. So our universe isn't a torus either, though. That means that our universe is neither a dodecahedral space nor a torus. And if that's the case, then it's probably hyperbolic. And that's why when you walk away from Earth, you're not coming back anytime soon.